Okay, so this is part 2, and this is taken from this survey paper we have, and these collaborators from Romania. These are the students of Professor Radu Ionescu, Aline, and Vlad. They have done a great job preparing this presentation, and I've been discussing with them. So as we did on Monday, so at a high level, diffusion models are probabilistic models used for image generation. They involve reversing the process of gradually degrading data. So there are two processes. One is a forward process. So we take the data and progressively add noise. Essentially, at the end, we destroy the data. And so this will be like this. So we have data distribution for our training data, and it can be any kind of distribution, mix of Gaussians or any other distribution. We will do the forward process. We'll keep adding noise. At the end, it will become the Gaussian distribution. Okay. So then there's a reverse process. We will start from the Eastern Gaussian and gradually remove the noise sequentially. And basically at the end, we'll come up with the sample from the original distribution. So that's a process, the forward process, reverse process. So there are 3 different methods. One is denoising diffusion probabilistic models, for short, DDPM. Second one, noise condition score network, which is NC SN, and the third one is stochastic differential equations. And actually, at the end, they can be related in the same framework, and they are very similar. And I'm going to show you that. So just look at examples. So we have an image X0, which we sampled from original distribution, the training distribution, training data, and we gradually add noise, and we come up with this image, which is complete noise. And this is a Gaussian distribution. The mean is 0. And the standard deviation is identity, or covariance matrix identity. So then we have the reverse process, where we start with the Gaussian distribution and gradually remove noise, and we end up with a sample from original distribution, which looks like the image. So now, how do we add noise? And this is the iterative process where we take the image at xt-1 iteration, and from there we generate xt. And this is modeled by this probability distribution. It's a conditional distribution, and this has the mean is shown in terms of beta t, and this is the xt-1, and then this is the identity matrix I, and this is beta t again. This is our covariant, this is our mean, so that is our normal distribution. So now what this is saying, that given xt-1, we can generate xt. It's a probability distribution which is iterative. We start with, say, 0, we generate x1. From x1, we generate x2, x3, and so on. It is shown here. Now, and then a beta t is a small number. So the image is replaced with the noise. Now we can do this actually in one shot, that we don't have to do iterative process, and which means that we can, given x0, we can come up with xt by this. So here now probability distribution again is normal, but the mean is this one, and then the covariance matrix is this one, and then beta hat is defined like this in terms of alpha and so on. Okay, so now we are more interested in the reverse process. With the forward process, we are going to train the neural network. The reverse process, we will actually use this neural network to do the inference, and inference basically means that we are going to generate the samples. Okay, so now the forward process was going from x0 to xt, uppercase T, and reverse process will go backward. We'll go from xt to xt-1, xt-1 to xt-2, and keep going up to x0. And that also is modeled by this distribution. So here now, as you see, is different. Given xt, you want to find out the xt minus 1. That's a reverse process. The forward process were given xt minus 1, we were going to estimate the xt. So now for this one, we will train a neural network. So whenever you see theta is a parameters of neural network. And that will give us this estimate of this probability. And that, we will model by the Gaussian distribution. This will be the mean vector, and this will be the covariance matrix. Okay, these are going to estimate. So they'll be approximated by a neural network. Now, and these theta is neural network weights. So now, so here we can actually we don't have to estimate the variance to simplify. We can fix the variance in all the iteration and just estimate the mean. And that also we can do. So, so now how do we train the neural network as we went through on Monday? So we are going to use what's called UNet, which is like the autoencoder is encoder and decoder. This is the encoder part, the first part, and this is the decoder part. So here we have an image, and the output will be also image, and it's used for semantic segmentation and all those things we went through in detail on Monday. So for us here, we have xt as input, and we also have t as input, and we are going to concatenate or aid that thing we talked about on Monday also. So at the end, we are going to get this mu theta, which is the mean of this distribution. And then we can take this normal distribution because the covariance matrix is fixed. And we got the mean vector from this neural network. And then we will sample from the distribution, and that will be our image xt minus 1. And we can keep doing that. So that is the way we are going to do. And we talk about how we will train the neural network, the UNet. So this is our objective function. So we want this neural network to estimate this z theta, and the input is xt and t, as I showed you earlier, and the ground to the zt. We want to come up with estimate as close as possible to zt. And so this we are going to do first, that we look at all possible training example from the initial distribution. So that's what this is. And then we will sample the ZT, noise from normal distribution, and we are going to do this for all times. So that is our objective function. And this is L simple, and we derive a lot of derivations we did at the end up with this one, which is very simple and more intuitive also. So therefore, training algorithm very simple. We are going to repeat these steps until convergence. So we will take the training example from our training distribution, x0, and then we will sample also the time from uniform distribution, and we'll sample the noise from the normal distribution, zero mean and identity as the covariance matrix. So then this is the way we are going to generate xt. Okay, so as you see, we start with x0, which is this one, and then we have this beta t hat and beta t here, t hat here, and zt, which is here. So that's why this beta t, beta t hat, and so on, they are important because they guarantee us that we can show that if we follow that, then we will end up with the normal distribution at the end. So it's not, we can just not take an image, just add a noise. We don't have to have. So we have to have those. So then beta t hat is like this in terms of alpha, and alpha was defined also 1 minus beta and so on. Earlier I talked about. So then if you look at little detail, so this is our objective function, L simple. And this is the, yes.
Sorry to interrupt you. So 1:1 is in waiting room.
Yeah. So so you want to enter him because if it's late, then maybe you should not.
Yeah, his Zoom is restarted. So can you let him in because it's not showing me on my side somehow?
Okay. Okay, please show up on time. Otherwise, you won't be able to come to this one. How do I do this thing? I don't see anybody's anticipated. Okay, just you know what you want me to do. So it's already 15 minutes late. So let him just skip, and then next time people will come on time. Okay, so let's continue this. Again, the little more detail. So we sample we sample an image from our data set, which is X0, and we choose the randomly a time step T of the forward process, and then we have the sample noise from the normal distribution, and then we generate XT using this, which involves the ZT and X0, the original initial one, and that will be noisy image, and then we will update the parameters of network, because we are going to differentiate the loss function with respect to theta and update the theta here. So that's traditionally what we do. Okay, now I see I can admit him. Okay, so then this is the process. So we are going to, so that was that we talk about was the training of the neural network. It's a training algorithm. So how do we train, which is in the way a forward process. Now we have done this training, then we'll do the inference, we'll input xt and t, and we'll get a z theta. Okay, we'll take that z theta, and then we pass the current noise image to the neural network, and we'll get the z theta, compute the mean of Gaussian, and this is the way we are going to generate the xt minus 1 from xt, and this is our Gaussian distribution. So this is our mean, it's centered at xt, this is our mean, and the covariance matrix is fixed. So essentially, neural network will give us z theta, which we'll put here, and all these other ones are the same as we are talking about. So it's a pretty simple process once you get it, that once the neural network is trained, we put xt and we get z theta, and z theta goes here, and then we have this probability distribution, and then we can sample from there, and that will become xt minus 1. And this way we can keep repeating, and we'll keep removing the noise and etc. So this is called sampling. So that was, I simplified what I covered in detail, all the derivation on Monday, but just to put in perspective what you need to know for denoising diffusion probabilistic model, DDPM. Now there's another method which is actually more interesting, which is called noise condition score network. Okay, so now as we have done so far, we have talked about probability distribution. We are going to estimate the parameter probability distribution. As you saw, we were estimating the mean of this Gaussian distribution, and we trained a neural network, UNet, and gave us the z theta, and we put in that standard formula of the normal distribution, then we can sample the distribution. Now in a score function, instead of estimating the probability density function, we are going to estimate the log p of x and the gradient of that. So we will not estimate the probability distribution, but we'll estimate the gradient of that. So that's different. But what this is going to do, it will simplify the process, and it's actually much better. So now, the derivative of anything, it gives you derivative or gradient of any function, give you a direction of a change. You guys know that the derivative rate of change, and if it's multi-dimensional, so it gives you direction of change. Even one dimension tells you whether it's positive or negative. So this score function essentially will give you direction. We need to change the input x such that density becomes greater. Okay, So here is the example. We have distribution, which is a mixture of two Gaussian. So there's one Gaussian here, another Gaussian here. So this is a mean of first Gaussian, and this is showing you these are the equal center circles where we have same probability. All these elements, this is X, this is Y, 2-dimension. So what is the probability that we will get some sample at this location? Sorry. So is high, and as we go out of the mean, as you know, in a bell curve, it reduces, and so on. So, but these are the equal list because this is now it's circular symmetric. The Gaussian in one dimension is symmetric around y-axis. The left and right is same. Now here is 2-dimension, so it is a symmetric around a circle. So this is one Gaussian, and this other Gaussian. So it's a one distribution mixture of two Gaussian. And so what the arrows are showing you are the score function. These are the gradient of this log p of x. We take the mix of Gaussian distribution, apply a log, and we find the derivative of that. So derivative, when we do a function which is more than one variable, then it is called gradient vector. It will be a vector. So in this case, here will be 2-dimensional vector with the gradient, which is shown by this arrow. Okay. So now, so second formulation of diffusion model is going to use score function. This is the gradient of the probability density function. So, and we are going to use what is called Langevin dynamics method, and where we start from a random sample, and we'll apply iterative updates with the score function to modify the sample. And then the result will actually be approaching to the true distribution P of X. And so score is gradient of logarithm of probability density with respect to input, as I said, because probability density functions of X, and we will find a gradient with respect to X, that's your delta X, the sign, and which is shown here. And this is our annealed Langevin dynamics. So what is showing that if we know the score function here, then we can get the xi from xi minus 1 by adding this and then this term. So now we'll go through what are these terms. So this is our score function. This is that. Okay, so that's what we're going to train a neural network now. The neural network will estimate that instead of what z theta was estimating previous method. Then we have here is a random Gaussian noise. This is the Gaussian noise, which is mean is 0 and the covariance is identity matrix. Okay, and then we have gamma, which is a step size. So that is the process we are going to go through to generate the xi from xi minus 1. Okay, so now the score is approximated with the neural network. So we're going to train a neural network which will give us the score function as theta. This, whenever you see theta in this thing, it means it's a neural network. And but the ground truth is this is what we want to estimate. Okay, so we'll minimize this error. So denoising score matching. So the way we are going to start, that we will have the sample x bar from the normal distribution, which will have the mean will be x, and then identity matrix, the covariance will be identity matrix with a fixed sigma. And then we are going to minimize this loss function with respect to that sample, and that will approach the true probability, the score function of the original distribution. So after training, S theta will approach the actual delta x log P of x. Okay.
Dr.
Yes.
Shah, I have a question. So this P of X,
can you just hold on? Let me finish, then we can answer your question. Okay?
Sure.
Just hold on. Remember the slide number, so we'll come back to that. Okay, so naive score-based modeling, it has a problems. Okay, so there was nice simple thing there, but it has problems. And what are the problems? The problem are the real data resides on low dimensional manifolds. So when we have in this situation, score is undefined outside those low dimensional manifolds. So data is concentrated in regions, certain regions. It's not actually throughout the space. So we will end up estimating this score function incorrectly in the low density regions. So now, therefore, this Langevin dynamics may not converge, and will only converge to high density region, and we need to fix that. So here's example. So we have the probability density function. Now, somehow we have a lot of samples here, a lot of sample here, but we don't have here. So then if we do the gradient of that density, so we will have all these gradients, the arrows. And in this area, when we have high density, we can estimate these score function correctly, but we'll have inaccuracy here. So that will be the problem. So we need to fix that. Okay. So what we are going to do, that we are going to perturb the data with random Gaussian noise at different scale, not just one scale, like we talk about sigma. So, which means we will have the sequence of these sigma 1, sigma 2, sigma 3, and so on. And that somehow will fix that. And we will estimate the score function via a single network, but we will have these several sigma values applied, noise with sigma values applied to the data, and that somehow will help us. So this will become like that, score function will become like that. Okay. So now what we are going to do, given a sequence of Gaussian noise of these scales, sigma 1, sigma 2 to sigma t, we will sample from that original distribution, which is our training distribution, training data, and with the sigma 1, we'll assume that's sigma 1, and we will then at the end up with the distribution, which will be a normal distribution, mean 0 and identity as the covariance matrix. So that is what we want to do. So this perturbation will be given by this. So we are given x, we want to get xt, and we will model by normal distribution, which will have mean at x, and then we will have the covariance fixed, which will be sigma t square and identity. So this is our normal distribution. As you remember, that this is what happens, xt minus x, all the square, sigma t, and 1 upon under root 2 pi, and all those things. So it must be familiar to you. So now we want to take the gradient of this. We want to differentiate this. Okay. Now, as you know, and differentiating, we want to first take the log of this, then we want to differentiate this. Now, as you know, that when you take the log of exponential, then exponential will disappear. Okay. And the derivative of this will be 2xt minus x upon sigma t squared. Then we'll differentiate this one. So it will end up like that, and you can verify that yourself. So now this is the score function of this distribution, which is xt minus x upon sigma t squared, and with a minus sign, so which is good. Okay, so therefore, when we train our neural network, our objective function will be this. Okay, we want the score function, the network, to predict this data where such that it is close to the ground truth, close to this thing. Now remember, whenever you have loss function, you do the minus. But since this was negative, as you see here, we have a negative xt minus x. So therefore, we have put plus here. So now we are going to do that. We will take the training example from this original distribution. Then we will take the different sigma values, and then we'll take a sigma t, and we'll do all that. That's the way we are going to train our network. Okay. So now, in addition to that, we will have this weighting function, which is called gamma, sigma t. So we will put weighting function for each different scale. So previously, what we explained, we want a weighting function. Now here, there'll be different, weighting function for different scales and be parameter, which we'll discuss that. Okay. So then now once we train this network, again, keep in mind, so we are training the network, which is like a forward process. Now our aim is to do sampling. Our aim is to do inference once it's trained, and we want to generate the sample, generate images. So that's why we are going to use now annealed Langevin dynamics. It's used in a lot in physics. So what we are going to do is we will have number of iteration for this dynamics, and we'll fix that. And we will have these noise scales, sigma 0 to sigma t. And we will update the magnitude, this coefficient I talk about for each sigma, gamma t. And so algorithm is simple. So we start with the normal distribution, zero mean and covariance identity, and we'll get this sample. And then we will have a loop for all different t from uppercase T to T minus 1, T minus 2, and so on to 1. And then we will have another loop for 1 to n, where I is index. And so first thing we will do, we will sample the noise, ZT, and then we will, given the xt at I minus 1th iteration, we are going to get xt at ith iteration. And this is where we are going to use the score function from our neural network. So we'll get that, which will give us this score function, and then we will add these coefficient here, and this is our noise, which we generated here. And we will keep doing this for n times. And then we will take this and we will, that will become xt minus 1. Because from xt, we want to generate xt minus 1. From xt minus 1, we generate xt minus 2 and minus 3 and so on up to x0. So that will be the sample generated. So again, at the end, the algorithm is very simple. So this is sampling. This is the way we are going to generate new image from that network. So then again, going in detail. So we sample some standard Gaussian noise, which is shown here. We start from the largest noise scale, which is denoted by time step here. Then we will do this loop for n iterations in the Langevin dynamics updates. We will have the get a noise, and then we'll update, and then we will get the next iteration, and that's it. So that is the way to sample to generate new images using the second method of score networks, and this is the second method of diffusion model. Okay, so now we can, in a way, compare the losses from this denoising diffusion probabilistic model with the score network. And as you remember, that here we were estimating a probability, but here we are estimating gradient of probability. So this was the one, loss function, which we call L simple. I just went through earlier. And this is the way we were using to train our network. And the network we're estimating Z theta, and the ground truth was ZT, and we were doing that. Okay. Now, for a score matching function, we are using this objective. So that will give us S theta, and this is the kind of ground truth. And here also we have this coefficient, the weighting function for different sigma. Now, so we want to compare. They're doing a similar things, which is the beauty of the sciences, right? So the main thing in science is how do you relate different concepts and unify, and you get Nobel Prize. That's what science is about. At the end, it becomes very simple. So now, so weighting function, L simple, we don't have weighting function, and they have done experiments. So if you just use one, it's better as compared to using weighting function. So therefore, now we want to relate these two objective functions, and we can say basically they are doing the same thing. So let's look at ZT, okay? Because ZT is what was the objective, which was kind of ground truth, which this network was estimating Z theta. So XT, as you know, is from the normal distribution with this mean and this covariance metric. So therefore, this is a distribution. So we will sample XT from this distribution. So that particular sample will become XT equal to X0 plus sigma T ZT, and ZT is the sample from the normal distribution. So this will become XT based on X0. Okay. So now if you look at this one, we can take the XT, take the X0 on the left side, so it becomes XT minus X0, and then bring its sigma T in the denominator, and that'll become ZT. And that's what we have here. So ZT is XT minus X0 sigma T. And this is being used in the L sample denoising diffusion model method for the diffusion model. And we are using XT minus X0 sigma T square in the score matching function. Since this was a negative, so actually, as you see, that they are basically same. So that's very, very interesting, right? So ZT is equal to this, and when you plug in ZT, so you'll get actually set. So these two methods, in a way, are doing the same thing, which is very interesting, very nice. We started very differently. In the first one, we are estimating the probability density function. In the second one, we are estimating the score function with the gradient of probability distribution. So which is very nice. Okay, so basically this S theta learns the negative of noise, which is minus ZT upon sigma T, because we have sigma T squared here. Okay, so now sampling. Now this was the way we were training the network. Now once we are trained, now we look at the sampling, because that's what ultimately we want. We want to generate new images. So sampling, if you remember from the denoising diffusion probabilistic model, this is the way we were sampling. So once we have Z theta, that becomes the part of the mean vector, and then we can take XT and use this and beta T, and this is the ZT, the random sample from the Gaussian distribution. And this is the way we are doing the XT, generating XT minus 1 from XT. So that's our sampling for the first method. So this essentially doing that, we are subtracting the noise. This is essentially a noise from the noisy image. We want to make it less noisy. Okay, so XT is noisy. We want to get XT minus 1, which is less noisy. So we are subtracting noise. And what this neural network is estimating Z theta, and we put in here to make it consistent with the Gaussian distribution. So which is very nice. Okay, now the scoring function, matching function. So this was the scheme that we are going to use, that we will generate the previous iteration, ith iteration from the ith minus iteration, get the score matching, and then we will use the ZT, our random, sample generated from Gaussian distribution, and these are the other factors, and that's what we have. Now, in a way, this is also true that because S theta is approximating the negative of the noise. Remember, I showed you minus. So we are actually subtracting the noise, this is noise, from this noisy image, as we are doing here. So it's again, it's very nice. So you can relate these two, which is very good. Okay, so therefore this was our loss function for the DDPM, and then this is the loss function. We can rewrite this because it's a minus here, it become plus, And then this is the last function for our, this is for score matching, and this is for DDPM. And this simple last function. So, this relating how we sample and what are the objective function that we kind of showed, they are similar thing. Again, they are very different approaches, but it is, very nice way that we can talk about that. Okay, so now, so therefore, the generator process defined by NC, SN, and DDPM are very similar. That's the conclusion here. Okay, so now we talk about two different ways to do diffusion model: denoising diffusion probabilistic models and noise condition score network. Now there's a third one, which is the stochastic differential equation, which is actually a harder one. So, and I won't spend much time, but just to give you a flavor. And all these three are actually related, which is very good. Okay, so now you guys have taken differential equation courses in your undergraduate, and the stochastic gradient, stochastic differential equation, but there's a noise. Stochastic noise is probabilistic. We are not deterministic. Okay, so it's a generalized framework that can be applied to our two previous methods, the two methods we discussed. But only difference here is that it's a continuous process, because these differential equations are continuous. The earlier we talked about, which are discrete, we do the loop I is equal 1, 2, 3, and time and so on. Okay, so now this method for generating the images works the same principle. So we are gradually transforming the data distribution Px0 into noise, and then we have a reverse process to obtain the original data distribution. Okay, so so the forward diffusion process in terms of the stochastic gradient differential equation is shown here. So we have x, the partial derivative of x with respect to t is equal fxt and sigma t and omega t. So now this we can rewrite like this. So with dt we go other side. So dx is equal fxt dt and sigma t and d omega t. So now these are the components. So this is called the drift coefficient, so which will gradually nullify the data x0, make it a noise. And this is the Gaussian noise with zero mean and the identity covariance matrix. And so that is the part which is stochastic, because differential equation don't have any noise, standard one. But now here we are adding the noise, the probabilistic. That's why it becomes the stochastic differential equation. Okay, so this is a function for diffusion coefficient, and it controls how much Gaussian noise is added. Okay, so now, so that was a forward process that we are going to add noise. Now this is the reverse process. That's where we want to actually generate a sample, and the stochastic differential equation for that is given here. So fxt, same thing, and then this is the noise derivative of that. But interesting thing is that again we have this score matching, this derivative of the probability, the gradient of probability. So you see this is kind of common theme in this, that if we can train a network which can estimate this, then we can use it in all these methods, which is very interesting, very nice. So therefore, the training objective is similar to the score matching network. And so here we want to, use the use the network to train, which will give us this S theta, and that, as you know, is the gradient of probability. And the only difference is that these differential equations are continuous, so we have to, take care of that. So score function is used in reverse time, implies neural network to estimate the score function, and uses numerical SDE solver to generate the samples. So we are going to actually solve this differential equation, Stochastic differential equation, numerically. And you must have heard about different methods to solve numerically differential equation, like run kata, and then there are many other methods. Okay, so now, so this is the process that now we are going to try to explain and see SN in terms of the stochastic differential equations, so, which is interesting. So as you remember that xt we were sampling from xt minus 1, and there was some mean which, we can say sigma t, or we can even write out like here to make it convenient. So it's sigma t square minus sigma t minus 1 square. So just because we are going to bring in this derivative here. So this is very similar to what we have been doing. So now, given this distribution, so xt will be generated from xt minus 1, and this will be these sigma and zt. Okay, so that's kind of roughly the way we are doing this matching score function method. So now we can take this xt minus 1 on the other side, and then this we can put everything there, and we just have done t plus and t minus we can do also, which is fine. They'll just become 1, and so what we have, and zt is there. So now it's becoming differential equations, right? So this is xt minus 1. So we can write down that partial derivative of x like this. And this is sigma t minus sigma t minus 1 divided by the interval. So this is a derivative of sigma. Okay, so that's what we have. And of course, this is, we can replace this with derivative omega t, which was our Gaussian noise. So therefore, this kind of appears very close to the stochastic differential equation we had. Only difference is that we don't have this one. And so what we have done, we started the second method, the score matching method. We reduced that to stochastic differential equation, which is very interesting. Okay, so that's what we end up with. And so now we can do the same thing for the first method, DDPM. So can we derive DDPM, from DDPM to our, stochastic differential equation? And we can do that also. So as you remember, the DDPM, that's what we are doing. So we have a distribution, we sample from the distribution, and this beta and all this thing, you know about it. So xi is 1 minus beta I, and xi minus 1, and all this thing. So you want to generate xi from the previous one, xi minus 1, with this ZIS noise. This is what we have been doing. Okay, so now what we can do to relate to this SDE, we'll do delta t is 1 upon t, and beta t delta t will be I. So we can then write down here. Now we are going to introduce t instead of I here. So here will be xt 1 minus beta t and delta t, and this is I minus 1, so our step will be delta t, so it will be x t minus delta t, and this under root, and we are replacing beta with beta t, delta t, and instead of zi, we'll have zt. So we are getting there. So now, interesting thing is that we need to take this and find this Taylor series. Okay, Taylor series, is very important tool which we'll use again and again in machine learning. And essentially, it's saying that we can get a linear approximation of any function. And if you do, and you should do this at home, and I'm going to maybe show you a couple of slides to motivate you, the Taylor series. So if you take the Taylor series of this, then we can actually simplify this. Taylor series of this will be this, only first order term. And then we have xt minus delta t, and this whole thing is same. Okay, so then we can simplify this further. So multiply this xt minus delta t here and here, and this same thing. Now we have xt and roughly equal to xt minus delta t. We can bring in this other side, and then remaining terms are same here. And then we can, change this in continuous domain. So this will become derivative of x, because we are taking xt, subtracting at xt minus delta t, which is change, which is partial derivative of x, and then we can do the same thing here, which is the beta t and xt, and partial dt, and then derivative of zt is the derivative omega. That's what our partial, the stochastic partial differential equation was. So that's amazing, right? So we started with the DDPM, we ended up with the SDE, and that's what SDE was. So which is very nice. So this way, we talk about three different methods: denoising, diffusion, probabilistic model, noise condition score network, and stochastic differential equations. They all in the same framework. We talk about their, the forward process, and we use a forward process to train the neural network. And then we use this neural network to do the reverse process. And reverse process actually give us a sample. In the forward process, we take an image from the training data, we keep adding noise, and we learn the parameters of network. In the first one, we are estimating a probability density function. In the second one, we are estimating the gradient of probability distribution. And the third one is very different, that we are explaining this in terms of stochastic differential equation. There's 100 years of literature on the how to solve the differential equation, stochastic differential equation, all these things. We are leveraging all that. And all these three methods can be related. The loss functions, the sampling, and I explained to you. So one last topic. Now, what we have talked about so far is the unconditional generation. We don't have any condition. We just have a data, we learn the network, and then we can unconditionally synthesize an image. Okay, so conditional generation is what is exciting. Condition means that you put a text and you want to generate that image. Okay, so or you want to generate an image of a particular class, that's your condition. So let's get into that. That's also it's very nice. Okay, so now, as we said, diffusion model estimate the score function in this gradient of the probability, and we then can sample from distribution. Now, if we want to have the condition distribution, so this is a conditional probability distribution. What's the probability I've given y? That's a y is a condition. Okay, so if we want to use a condition, then we need to actually train a network which will estimate this instead of this. Okay, so solution one will be that we'll train the model with an additional input y to estimate this, okay? And which will be like this. So we will have the same U-network, unit time we have inputting, and at the time we'll input the y. What is the condition? Then this will estimate the score function for that conditional probability density function. Probability PT of xt given y. So this was just PT. Now here we have condition y. So that's one approach. Okay. So now in this case we will standard model will estimate the this distribution from using the sample from PIX. Now, if we want to use a condition which require this one, and that we need to do the score function, that's probability density function. Now that was the first solution, and the second solution is that we can have the classifier guidance. And this is very interesting actually. So what we are going to do is apply this Bayes rule to actually relate this conditional generation with the unconditional generation. Okay, so let's look at and listen to this carefully. So you guys know the Bayes rule, which relates the two conditional probability. So here we have the probability of xt given y, which we can compute from the probability of y given xt. Okay, so typically this is called prior probability, this is called posterior probability, and these are other terms: probability of xt, probability of y. That's a very standard thing. Bayes rule, you should know this. So now in their case, y is the condition. Okay, so it can be class, it can be text, and so on. So we want to kind of manipulate this and come up with something interesting. So what we are going to do, since we always use the logarithm and the gradient, so we'll take a log on both sides, log of xt, y, and log of pt, y given xt, and plus, because product multiplication become plus and log the xt, and this a division, so it'll become minus, like that. So it's pretty easy. So now we are going to take the gradient of that, because that's what we want to estimate, this one here. So when you take a gradient, then as you know, that this one does not have any xt. There's no xt. So this is like a constant for xt. So therefore, this will become actually 0. So therefore, this gradient of this conditional probability have these two terms: the probability of y given xt and probability of pt, which is unconditional. Okay, so now that's unconditional diffusion model. That's what we have been doing, score matching. And this one is the classifier. So we can train a classifier which will, given the xt, will give us a class, and then we can combine these to do this conditional class generation. So this is a classifier guidance. Okay, so that's what we do. So what we do, that instead of just taking this as it is, we are going to use this factor s here. So this will multiply by, this factor will multiply by s, which is a conditional probability, and this with 1. And that will be guidance weight, how much weight we want to give it to the condition, how much unconditioned. And so when you use the equal, then you can generate these kind of images, but when you use more importance of the condition, then you can generate better images of this particular class. Okay, so this basically Y here is that class. So now the problem is that you need to have these gradients estimate each step of denoising process, because the unconditional denoising we were doing is easy, we have learned and so on, but now we have a classifier, so that's we need to have this robust classifier and so on. So it's a problem, and training of classifier on noisy data which can be problematic. So they found out a very nice solution. And so what that does, so we start with this, and then we apply again Bayes rule. So Bayes rule is so important, it's so intuitive. So now we are going to apply Bayes rule, probability of Y given xt. Again, the same thing. So this would be given by probability of xt given Y and probability of Y and divided by probability xt. So then we will expand this. We will take a log on both sides, log of this, and then we will have log of xt, because this is a denominator, and this is log of pt, which is here, plus. So there's a log of this thing. Okay, so now we take gradient again. So gradient on all sides, and again this one doesn't have xt, so it becomes 0. So this is the gradient of this thing, gradient of Y given xt. Okay, so now what we're going to do, we will take this, and here yxt, for this one we are going to put this expression to simplify. So this is our top one here, and we are going to substitute this expression here, and it will become like this. So S, so instead of this, we'll put the gradient of log pt xt given Y in this one, and then this will remain as it is we have. So now, as you can see, that we have two terms here with log of probability g xt, this one and this one, and gradient of that. So we can combine those. So that's what we are going to do. So this will become S, and this will become 1 minus S. Now we have the unconditional probability here, and this is a conditional probability. So this is what we are going to choose, and what we are going to do is that we will actually have a single network. We won't have two networks. We will have single network, and which will learn both, and which is a pretty brilliant thing they did. So what's going to happen, we will have t and y, which is the condition, but what we are going to do is sometime we will have condition null, which will be y become all zeros. When condition is null, then basically we are using when it's a null, it is this unconditional probability, which was this term which I showed you here. This one, this is unconditional. So there's no condition. So we'll put y all zeros and become null, and we will do sometime we will use y is null, and some other time we will do y whatever we have, because as you know, this one is S, other is 1 minus S, so they are balanced. So therefore we can just train one network which will be classifier-free guidance, so it doesn't need a classifier, separate classifier, and it actually works, which is really nice. So that is your condition thing. Okay, so now one last thing, then I'll stop. So now all these things can also be related to CLIP. That's the reason I covered CLIP in the class. So what these guys, and this actually we're going to discuss in the next paper, the first paper, glide paper. So as you recall, the clip model takes the caption, which is like this, and the image, learns the text encoder and image encoder, and do the contrastive learning. And it does by cross entropy, and it gets the similarity between an image and corresponding caption, and then minimize the similarity between the image and all other captions, not the that same caption for that. And similarly here, maximizes the similarity between caption and image, but here then we take the different values of these. Here we are changing the text, and here we are changing the images. So here, whatever the text we use for this particular image, we want to maximize, and the text for all other texts we want to minimize. That's a contrast loss. One cross entropy term, other cross entropy term. So we have done that. We have discussed this thing, and it's very, very powerful. Now, what they found out, that the optimal value of this, is actually optimal value of this similarity between the text encoding and the image encoding is this one, log P of XC, which is a joint probability of the image and the caption divided by the probability of X and probability of C, and log of that. So we may have time to discuss that when we discuss the paper, but this is pretty interesting. So now you can write down like this, and then what they are doing, that you can do this conditional image generation with a clip guidance instead of class-free or class guidance, as we discussed earlier. So what that means, that remember, this is what we are doing, the classifier guidance or classifier-free guidance. So we have the XT given Y and XT. This is the unconditioned, this is condition, and we have these factor S minus 1. Now, what we can do, take this one, and of course, here was a condition Y. Now here our condition C, which is a caption, so which is okay. So we just replace Y with C. So now we can take, since we are taking the gradient, so we will take this XTC and we'll add some additional term, log of PC, okay? Since this doesn't depend on XT, got the gradient of XT, so that's fine, we can do that. The gradient of this is 0, so this is same thing. This and this is same thing. We can do that, okay? And then 1 minus A is like that same thing. So now, as I showed you, that this actually can be replaced by FXGC. So this encoding of image and this encoding of the text we get from there. So what they did in the glide, they actually trained the network with using the encoding embedding from the clip model and without this, classify guidance. And we'll discuss that in glide model. Okay, so I think that's kind of end the discussion. And so just one more slide. So as we have discussed so far, so we have unconditional image generation and we have conditional image generation. And we have been looking into important thing is image quality, how realistic the images are, and that's a surprising thing. Everybody's after that. But one problem with these diffusion model, and we'll find out that, is that they take a long time. So that's the issue. So that's actually the current research direction, that how can you come up with a simpler, quicker method. And they've made a lot of progress, especially stable diffusion and so on. So conditional image generation, we have done text to image. Now is the time that we are using the diffusion model to actually solve the computer vision problem. But image generation is okay. I mean, you can, generate an image and so on, but that's not a computer vision. Computer vision deals with, you want to analyze an image, okay, real image. So for example, image editing, even based on text, and then super resolution and image segmentation, and anomaly detection and medical imaging. So these will be the problems which I think will leverage all what we are learning here. So, and video generation is another good topic, because images are easy, but when you go to video, it's difficult because we have so many, frames and so much data and so on. Okay, so that I think ends